Standard 12 Chemistry Unit 9 Coordination Compound Part 1. First of all, let's see the complex compound. Let's start with the example. Here in square bracket, cobalt metal atom which is bonded with ammonia 6 times, and here it is charge is 3 plus, and out of the square bracket 3 Cl minus. Here the cobalt which is metal atom, and here the ammonia is neutral molecule. In another example, cobalt which is bonded with cyanide ion, and that is 6 times, and its charge is 3 minus. So cobalt is metal atom, and here the cyanide ion is anion. So by these two examples, number 1 and number 2, we can say compound in which metal atom bound to the number of neutral molecule or number of anions, and they are bonded by sharing of electron, and these compound are said to be as complex compound, or in modern terminology it is said to be as coordination compound. Here the some metals are bounded as complex, like magnesium in chlorophyll, iron complex in hemoglobin, or cobalt in vitamin B12. It is important for MCQ or competitive examination also. Now the applications are the most of the complex compound used in electroplating, or in textile industries, for dyeing, or in medicinal chemistry. Alfred Werner proposed the theory of coordination compound. So here the Alfred Werner's theory of coordination compound, he proposed the concept of primary valence or secondary valence for metal ion, secondary valence for metal ions. Here the binary compound like chromium trichloride and its primary valence is plus 3. Here the for chloride it is minus 1, and here the for chromium its charge is plus 3. Then after COCl2 cobalt chloride and its primary valence is here plus 2 charge, and for chlorine it is minus 1 charge, so its primary valence is plus 2. Same is in palladium chloride PdCl2 Pd and its valence is plus 2. Now based on the experiment, cobalt chloride, in cobalt chloride some amount of ammonia is added, and into this silver nitrate is added. The complex we get COCl3 and 6NH3 with yellow color, and the 3 mole of silver chloride is in white PPTS is obtained. So here the all chlorine which is bound with the silver. Now in another experiment, COCl3 and 5NH3 which is in purple color, and 2 moles of silver chloride is formed which is in white color PPTS. Here the only 2 moles of chlorine which is bonded with silver, and then in another third experiment, COCl3 4NH3 and 1 mole of silver chloride is formed which is in green color and white PPTS. In fourth experiment, COCl3 and 4NH3, but it is in green violet color, and 1 mole of AgCl is formed. Here the complex cobalt which is bonded with 6 molecules of ammonia and its charge is 3 plus. Here the cobalt and 6 ammonia molecule which is bonded, three plus. Here the cobalt which is central metal atom and the 6 which is bonded with another 6 molecules of ammonia. So its coordination number is 6 and they are in octahedral shape. Here in square bracket, in a square bracket, it is single entity, or and this single entity does not dissociate, while in secondary valence number of groups bound directly to the metal ion, or it is said to be as secondary valence. From this experiment, the main postulates of Werner theory, the coordination compound metal shows linkages. Number 1 is primary and number 2 that is secondary. Here the first postulate, the coordination compound metal shows two linkages. Number 1 is primary, number 2 is secondary. Second postulate, that is based on oxidation number, or it is primary valence, and this primary valence is ionizable and satisfied by negative ion. So it is nothing but the oxidation number. Third postulate, that is secondary valence, and the secondary valence are non-ionizable, and it is satisfied by neutral molecule or negative ions, or it is said to be as anions. So here the secondary valence is equal to coordination number, and they are fixed for metal. For example, here cobalt, Cl, NH3 5 times, its charge is 2 plus and twice Cl minus. So here is the primary valence, or they are not dissociate. In a square bracket, the entities single, and they are single entities and they are not dissociates. And second thing is, here the cobalt which is bonded with chlorine and 5 molecules of ammonia, so 5 plus 1, that is total 6. So as per this, its coordination number for cobalt, its coordination number is 6. But after sometimes it is proved that the metal possesses more than one coordination number, like sometimes cobalt that possesses plus 4 coordination number and plus 6 also. Okay, then after fourth postulates based on spatial arrangement, ions or groups, ions or groups bound by secondary linkages to metal have characteristics spatial arrangement corresponds to different coordination number. Here the spatial arrangement, and it is called polyhedra or polyhedron. Here the species within bracket this in square bracket, and that is coordination entity, or it is said to be as complex or coordination entities. And the ions outside the square bracket, and it is called counter ion. For example, in the square bracket, cobalt, which is bonded with 6 molecule of ammonia, Na3 6 times, its charge is 3 plus, and here 3 Cl minus. Here in square bracket, the species with square bracket, and it is said to be as complex. And here the chloride, which is outside of the square bracket, that is called counter ions. So these complex are not dissociates. The counter ions can dissociates. Here the some octahedral entities. In square bracket, cobalt, Cl, NH3 5 times, and its charge is plus 2. Here the cobalt, which is bonded with 1 chlorine and 5 ammonia molecule, so its coordination number is 6. Here cobalt, Cl2, NH3 4 times, this charge is plus 1. Here the cobalt, which is bonded with 2 chlorine atom, and here the 4 molecules of ammonia. Here it is in octahedral shape, and this coordination covalent bond. Now the difference between double salt and complex. For example, carnallite, this potassium chloride, magnesium chloride, hexahydrate. Here the double salt carnallite is double salt of potassium chloride and magnesium chloride and 6 moles of water, so it is named as hexahydrated compound. And here the complex K4 FeCN6. Here the this entity in square bracket which is not dissociate, while potassium is dissociated because it is said to be as counter ion also. Another example is more salt FeSO4 ferrous sulfate NH4 twice SO4 hexahydrate 6H2O. Ferrous ammonium sulfate, or it is said to be as FAS. The next is potassium, and its chemical formula is KAL potassium aluminum sulfate SO4 twice 12H2O. These all are these double salts are dissolved in water, completely dissolved in water, while the complex these entities are not dissociates. Dissolved in water, that means it is completely dissociates. In potassium chloride MgCl2 hexahydrate is carnallite and react with sodium cobalt nitrate, it gives yellow PPTS, and this yellow PPTS is due to potassium ions, while the carnallite, which is and the some react with ammonium carbonate, or ammonium carbonate is added to the solution of carnallite, white PPTS is obtained, and it is due to sulfate ions, sorry, here the magnesium ion, or here the carnallite react with silver nitrate, white PPTS is obtained due to chloride ions. In more salt, or it is said to be as FAS, FeSO4 NH4 twice SO4 hexahydrate. In FeSO4 it is dissociated into Fe2 plus ion, it is dissociated into ammonium ion, or here it is dissociated into sulfate ion. Some amount of NH4OH is added, the green PPTS is obtained, and that is due to Fe. Nessler reagent is added, and the red brown PPTS is obtained due to ammonium ion that will confirm the NH4 plus is present, and the barium chloride BaCl2 or barium nitrate is added. The white PPTS is obtained that confirmed sulfate is present, while potash alum Kal SO4 twice 12H2O, which is dissociate into K plus Al3 plus and SO4 2 minus ions. Okay, so this is the concept about basic difference between complex and double salt. Next time we will discuss another topic. Thank you very much.